This is going to be just an introductory predicting products. I'm not going to go into solubility rules or activity series or anything like that. If you have no idea what I'm talking about, don't worry about it. It's probably coming in your own class. And so just simply looking at what the reactants are and looking at what the products would be, assuming that the reaction does in fact take place. So not all of the reactions that we do today would actually take place, but we're not worried about that right now. So your types of reactions. What we're going to do is learn how to predict the products in the simplest form of the reactions of each type. We're not going to do the big complicated synthesis reactions where you have a compound plus a compound combining to make an even more complicated compound. We're going to stick to the very basic predicting products, but you will need to be able to just simply identify the type of reaction for your more complex reactions, but I won't expect you to predict the products on those. So the first one is synthesis. We are going to be predicting the products of binary compound synthesis. Basically, all you have to do is look at the elements that are acting as the reactants, figure out what ions are going to be made, crisscross to make your product, and there you go. So here's some examples. Barium metal is reacted with solid sulfur. So barium metal, pure barium, would be Ba, and that, of course, would be a solid, is reacted with plus solid sulfur. Sulfur is one that tends to confuse people because they're like, oh, okay, I just write an S. But solid sulfur, pure sulfur, is actually 8 sulfur atoms bonded together. It's kind of like extreme version of Brinkelhoff, but this is a solid. And so these two guys, you're going to heat the bejesus out of them and force them to bond with each other. And the compound that you're going to make, you need to figure out, well, what ions are these guys going to make? Well, if you look at the periodic table, you'll see that barium is in group 2, so it's going to make a positive 2 ion. Sulfur is in group 16, so it will make a negative 2 ion. So super nice whenever the oxidation numbers are the same numerical value, just opposite in sign, that they just automatically cancel each other out. So the formula for the product of this reaction is going to be BAS, and of course if you have a solid plus a solid, pretty good indicator that you're going to get another solid. And this would be called barium sulfide. The next example we have, magnesium metal reacts with bromine. So magnesium, Mg, is a solid. Oh, hey, you know what? Forgot to balance this guy. So let's see. Put an 8 here for the sulfur, and then the barium also needs an 8. So magnesium metal reacts with bromine, and don't forget, whenever you're dealing with pure bromine, bromine is a part of Brinkelhoff, so you need to double it up. If you have no idea what Brinkelhoff is, it's the word, I did not come up with this, somebody way smarter than me did it, to help you remember the 7 elements that when they're a pure element, they actually double up. And so for bromine, instead of just being Br, it would actually be Br2. So, and bromine at room temperature, which if they don't give us the conditions of the reaction, we can assume that they are happening at room temperature. Bromine at room temperature is a liquid. So we're going to react these two guys together, and we are going to produce, if you put magnesium and bromine together, you get magnesium bromide, and magnesium is in group 2, and so it is going to form an ion with a +2 charge, just like barium. They're in the same group, so they're going to have the same charge. And bromine is in group 17, so when it ionizes, it becomes a -1 charge. So the formula for magnesium bromide is going to be MgBr2. And because this is an ionic compound, it's going to be a solid. If you're confused about how to write formulas, then you'll want to go either review how to write formulas on your own, or just Google search or YouTube search formula writing, and I'm sure that there will be tons of videos to come up. I think I have like 3 or 4 videos for formula writing, so just pick one and watch it. For decomposition, again, we're going to stick to binary compounds. So if I ask you to predict anything on synthesis or decomposition, I'm only going to ask you to predict for a binary compound. So basically for a decomp, all you have to do is look at the binary compound and figure out what elements are in it, and then write those elements in their natural state. So here's our examples. Solid silver oxide is heated. So first thing we need to do is write the formula for silver oxide. Well, silver is a transition metal with the symbol Ag, but it's one of the transition metals that actually doesn't have multiple possible oxidation states. Silver can only be a +1. And then oxygen, is in group 16, and so it will have a -2 charge. So the formula for silver oxide will be Ag2O, and it was a solid. And it's going to react, and it said it was heated, so let's put our little triangle there. And the products of this reaction, we're just going to break this guy apart into its individual elements. So one of the elements is going to be pure silver, and it'll be a solid. And then the other element is going to be oxygen. Remember, oxygen is part of Brinkelhoff, so it's going to double up. And oxygen is going to be a gas that's going to actually be released in this reaction. So now we have to balance it. And let's see, we got 2 silvers, we got 1 silver, so let's plop a 2 here. And we got 1 oxygen, we got 2 oxygen. So actually we need to put a 2 over here, which means we need to change this 2 to a 4. That's why you always balance in pencil. Water undergoes decomposition. So the formula for water, of course, H2O, and it is a liquid. Undergoes decomposition, which means it falls apart into its individual elements. So the first element is going to be hydrogen, which is a gas, and oxygen, which is also a gas. And then to balance this, we got 2 hydrogens here, 2 hydrogens here, so those are good. We got 1 oxygen there, 2 oxygens there, so let me put a 2 out front right here, which now makes us have 4 hydrogens, so I need to put a 2 right there, and we're done. For a single replacement reaction to predict the products, the first thing you need to do is identify the similar element in the compound that, and I hate using the word it without identifying what it is, that it is the individual element. Remember that a single replacement is an element plus a compound. So whatever the element is, it's going to replace an element in the compound that's similar to it. So if the element is a metal, well then it's going to replace the metal in the compound. Or if the element is a non-metal, then it's going to replace the non-metal in the compound. So identify whatever the similar element is, figure out what ions are going to be made, and then crisscross or cross over to make your new compound. And of course we have examples coming. Zinc metal is added to a solution of lead 2 nitrate. So we have zinc metal, so I'm going to put Zn, solid, is added to a solution of lead nitrate. So lead, Pb, they tell us right here it's a +2 charge, and nitrate, the polyatomic ion, has the formula NO3 with a -1 charge. So the formula for lead 2 nitrate is going to be PbNO3 2, and that's aqueous because the question said it was. And then we're going to react this. So look at zinc. What is zinc most similar to in this compound? Well, zinc is a metal, so it's going to take the place of the metal here. Well, obviously, lead is the metal. So zinc is going to take the place of lead. But in order to write the compound formed between zinc and nitrate, we need to know what charge zinc is going to have. And zinc is a transition metal, but just like silver, zinc doesn't have multiple oxidation states. It's only got one. And the only oxidation state that zinc, besides 0 of course, but the only charged oxidation state that zinc is capable of doing is a +2. So the formula for zinc nitrate is going to be ZnNO3 2, and it will be aqueous. Plus, the lead is now going to come out by itself, so it's just going to be solid lead, like that. And then to balance this, I always start with my metals, so 1 zinc, move on to my next metal, which is lead, so I've got 1 lead here, 1 lead here, and then my polyatomic ions, you'll see that I have 2, right here, 2 nitrates on the reactant side, and I also have 2 nitrates on the product side, so this reaction was balanced. Yay, kind of like it when that happens. Sodium iodide is added to chlorine gas. So here's our compound, here's our element. So sodium iodide. Sodium is Na with a +1 charge. Iodide is I with a -1 charge. So the formula here is just going to be NaI. And it doesn't indicate what state this is, so we just assume that it's at room temperature. Doesn't say it's dissolved in water, so sodium iodide is an ionic compound, which means it's going to be a solid, is added to chlorine gas. Well, chlorine is the element, and it's Brinkelhoff, so it's going to be Cl2 gas. Chlorine gas is also known as mustard gas. Do some World War I research on that, and some nasty stuff. So look at chlorine. Chlorine is the element. Which of these two elements is chlorine most similar to? Well, that should be pretty obvious. Chlorine and iodine are in the same group, so chlorine and iodine are going to be the most similar. And to know the formula that's going to be formed between, or the compound that's going to be formed between sodium and chlorine, well, chlorine is in group 17, so just like iodine, it's going to have a -1 charge, and you're going to form sodium chloride, also known as salt. Pretty likely that it's going to be a solid. And we are going to add to that, the chlorine is going to kick out the iodine, so you're going to have pure iodine, and iodine is a part of Brinkelhoff, and so you're going to have 2 iodines. And the state of iodine, obviously it's either going to be a solid or a gas, and at room temperature iodine is a solid. However, it sublimes, which means it phase changes into a gas at not a very high temperature, and so questionable about whether iodine is going to be a solid or a gas. Doesn't really matter anyways. So balancing this out, starting with my sodium, because like I said, I always start with metals. I have 1 sodium here, 1 sodium here, so they're good. Moving on to my iodine, because that was the next element that I got to. I have 1 iodine on the reactant side. I have 2 iodines on the product side, so put a 2 in front of the NaI. And then moving on to my chlorine, I know that that messed up my sodium, but I'm just going to keep on going, and then at the end I'll recheck it. I have 2 chlorines here on the reactant side. I only have 1 on the product side, so I'm going to put a 2 in front of the NaCl, and you'll see that adding that 2 right there actually took care of the balancing for sodium. So that one's done. Predicting products for a double replacement is actually pretty similar to a single replacement. Basically, you need to identify which ions are going to switch places, find out what ions you're dealing with, and then do the crisscross to make your new compounds. So, if I can get to the next slide, we have silver nitrate and sodium chloride solutions, which means everything is going to be aqueous, are mixed. So, I'm going to look at what I got here. I got a silver, which is an Ag with a +1 charge. I got a nitrate, which is an NO3 with a -1 charge. So the formula that's going to be made for silver nitrate, it's a +1 -1, so it's a 1-to-1 ratio. AgNO3, and it is aqueous. Plus sodium chloride. Hopefully I don't have to talk too much about that one, that you just automatically know it's NaCl. But just to hit it home, sodium does form an ion with a +1 charge, and chloride is Cl with a -1 charge, and it is also aqueous. Now that yields, what are we going to swap places? Well, we need to swap the elements that are similar, and with a double replacement, it doesn't matter if you switch the cations or the anions. Just do one or the other. Be consistent too. That just helps you kind of keep track of everything. So I typically switch the metals because, you know, they're the first things listed, so they're the first thing you get to. So I'm going to make a compound. I'm going to switch my silver and my sodium. And so one compound I'm going to make is sodium nitrate. Well, sodium's a +1, nitrate's a -1. So 1-to-1 ratio, NO3, and it is still aqueous. Plus, I've got silver with a +1 and chlorine with a -1. So again, a 1-to-1 ratio, AgCl. Now you're probably thinking, okay, that's aqueous because I got aqueous plus aqueous. But remember when we were talking about what a precipitate is? It's the formation of a solid from the reaction of 2 solutions. And so silver chloride is actually a precipitate. Now I know that my guys haven't learned about solubility rules yet. That's coming. But if you already know your solubility rules, then you know that silver chloride is a solid. And if you haven't learned solubility rules yet, I'm pretty sure that they'll be coming. And by the end of the week, my guys will understand how this is a solid. And so balancing, nice thing is, when everything has the same charge, that means the reaction is going to be naturally balanced, which is always super nice. Okay, next one, solutions of magnesium fluoride and potassium hydroxide are mixed. So, same thing that we did up above. Magnesium fluoride. Well, magnesium is Mg. It's in group 2, so it's going to have a +2 charge. Fluoride is F. It's in group 17, so it'll have a -1 charge. So the formula for magnesium fluoride is going to be MgF2, and that would be aqueous. Plus, and is plus. Potassium is K. It's in group 1, so it'll have a +1 charge. Hydroxide is a polyatomic ion, OH, with a -1 charge. So they have equal but opposite charges, which means the formula is going to be KOH, and it is aqueous because it said so right there. And then these guys are going to react. And again, switch the ones that are similar. So either switch your cations or switch your anions. It doesn't matter, again, which one you do because you're just going to end up at the same place. So I'm going to go ahead, and you know what, this time I'm going to switch my anions. So I'm going to switch my fluorine with my hydroxide. So my hydroxide is going to come over here and bond to magnesium. So magnesium is still a +2, hydroxide is still a -1. So my formula is going to be Mg parentheses OH parentheses 2. And this one is also going to still be aqueous, although just slightly so. Again, right now, don't worry about why. You'll learn your solubility rules later. And then the potassium is going to bond to the fluorine. Potassium is still a +1, and fluoride is still a -1, so the formula for that is going to be KF, and this is also going to be aqueous. And now we need to balance this little guy, starting with your metals. We got 1 magnesium, 1 magnesium. My next metal is K, so we got 1 potassium on this side, 1 potassium on this side. Moving on to my non-metals, not including oxygen, hydrogen. I always leave these guys for the end. Oh, actually, take that back. After metals, I do polyatomic ions that go from one side of the equation to the other without breaking apart. And since my hydroxide stayed together, I'm going to balance it as 1. So I've got 1 hydroxide on the reactant side, and I have 2 hydroxides on the product side. So that means I need 2 KOHs. And again, I know that I just messed up my K, but I'm going to keep on balancing, and it's probably going to work itself out. So now I've got my metals balanced, almost. K's out of whack. Hydroxides are balanced. Now I'm going to take care of my fluoride. So I have 2 fluorides on the reactant side. I only have 1 fluoride on the product side, so I need to put a 2 out here. And you'll notice that that just took care of the potassium. So yay. The 5th and final type of reaction that we're going to talk about here is combustion, and that's the reaction of any element or compound with oxygen. The products are based on what elements exist in the reactants. Basically, whatever oxygen is reacting with, it's going to bond to. So if you have a hydrocarbon, then you're going to have a carbon-oxygen compound in the products, carbon dioxide, and you're going to have a hydrogen-oxygen compound in the products, water. Whereas if you don't have carbon, no carbon dioxide, no hydrogen, no water. And that'll make sense in just a second. So you have methane, formula CH4, burns in air. Well, methane reacts with oxygen, so you have CH4, which is a gas, plus oxygen, which is also a gas. To produce, if you have gas plus a gas, it lets you know that everything on the product side is going to be a gas too. And so the oxygen is going to get with everything that it's burning with. So oxygen is going to bond to carbon and make CO2. And oxygen is going to get with hydrogen and make water. And it will originally be produced as water vapor, but depending on the surrounding conditions, it will probably instantly condense into a liquid. So balancing this guy, I'm going to start with my carbon. Got one carbon here, I got one carbon there. For my hydrogens, I have 4 hydrogens here. I have 2 hydrogens on the product side, so I'm going to stick a 2 right there for a total of 4, so that it matches out. And then here I have 2 oxygens. On the product side, I have 2 oxygens here. I have another 2 oxygens here for a grand total of 4, so I'm going to stick a 2 right there, and then we are balanced. Then we have magnesium metal reacts with oxygen in the air. So the magnesium is what's being combusted this time. So it's magnesium solid reacts with oxygen in the air. Oxygen's gas. And so oxygen's going to get with the one thing that it's reacting with. And so not only is this a combustion reaction, but it's also a synthesis. And magnesium oxide is an ionic compound, so it will be a solid. And then balancing this, 1 magnesium, 2 oxygens, 1 oxygen, so I need to put a 2 out front, which means I need to put a 2 on my magnesium. How did I know the formula for magnesium oxide? Well, I know that magnesium in group 2 forms a +2 charge, and I know that oxygen, group 16, forms a -2 charge. So they have charges that naturally balance each other out. And I have lots of examples, but I'm going to go ahead and call this video quits because it's really long. So I'll come back and get the rest of the examples.